How are we doing today? Hopefully y'all are doing well. So we are going to be continuing our notes on chemical reactions today. And we're going to be covering net ionic equations and representations of reactions. Okay, now for this, you do need to make sure you've got your notes, something to write with, and then you will also need a periodic table. All right, but otherwise, let's go ahead and dive on into these notes. Okay, so first off, what is a net ionic equation? Well, a net ionic equation is essentially what's going to show us what's actually reacting in a chemical reaction, because not everything is actually participating a lot of times. A lot of times we'll see some things that are actually doing something, and other things are just kind of there. They're just kind of spectating. We're going to call them spectator ions, but there's some things that are just doing nothing in the chemical reaction. So let's actually take a look at how we get these net ionic equations, these NIEs. Okay, so the very first thing that we should be doing is we should write the molecular equation for the reaction. Okay, so we're going to start with a chemical reaction, and we're going to be given probably just the reactants. And then after we take those reactants, you're going to be asked to predict what your products would be, and then you're going to need to write a balanced chemical equation for that. Okay? So typically what you're going to be told is that you are starting with a solution of the substance. Now, what that tells you is that it is already dissolved in water. Okay, so that's just something to kind of keep in mind. That tells you that it is aqueous. Okay. Now, once you've got that information, once you've got your actual molecular equation written, the next thing that you're going to need to do is identify what is soluble and what is not soluble. Okay. So for this, there's a couple things you're going to have to keep in mind. First off, if you've got a strong acid, a strong base, or a soluble salt, it is going to be aqueous, unless they tell us that our soluble salt is a solid crystal. Okay, so if they tell you that it is solid, then you'll write it as solid. If they don't, then you would have to assume that it's going to be aqueous. Okay. Now, for this, you are going to need to know your solubility rules, okay? And so this was actually something that we covered in last unit. We talked about the solubility rules of our salts. And so for those, the rules were, first off, group 1 and ammonium. If you've got a compound that has group 1 or ammonium, it is soluble no matter what. The next rule says all nitrates, chlorates, perchlorates, and acetates are soluble no matter what. Next are halides. So chlorides, bromides, and iodides. They are soluble unless they're paired up with silver, lead, or mercury 1. The last rule is all sulfates are soluble unless they're paired up with silver, lead, mercury 1, calcium, strontium, or barium. So those are your solubility rules for your ionic compounds. Everything else we assume is insoluble. Okay, so you assume everything else is insoluble. Next, strong acids and strong bases. For strong acids, there are only 7. So it is easier for you to just remember those 7. So those 7 are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, chloric acid, and perchloric acid. So these 7 right here, 5, 6, and 7. I've always remembered these by saying so, no, clo, brickle. For some reason that helps me remember them. I just remember that so is going to be my sulfate, clo is going to be my chlorate, the other clo is going to be my perchlorate, no is going to be my nitrate, and so on. All right. Now, the next is your strong bases. Strong bases are going to include hydroxides that are paired up with a group 1, except for hydrogen, because if it's a hydroxide paired up with hydrogen, it's water, right? And group 2, unless it's paired up with magnesium or beryllium. So how I remember this is strong bases are hydroxides paired up with group 1, except for the first one, and group 2, except for the first 2. Okay, so group 1 would be everything except for hydrogen, and group 2 would be everything except for the first two, which would be beryllium and magnesium. Okay, so you are going to need to know what your strong bases are, your strong acids are, and your ion or your soluble salts are. Okay. All right. Now, you do not ionize covalent compounds. So if you've got something that is a covalent compound, for instance, CO2, you would not ionize it. Why? Because there aren't ions in it. Once you've got that, you're going to remove your spectator ions. Something to keep in mind, though, is your exceptions. Okay, so if you remember last class, we talked about exceptions when we did the double replacement, right? Remember we talked about 3 different compounds that when they go through double replacement, they are going to decompose further, right? And those were ammonium hydroxide, carbonic acid, and sulfurous acid. So those 3 things, you are going to need to remember that they break down further. And that is what you are seeing right here. So if you produce one of these as a product, you need to remember that you are going to break it down further into, like with ammonium hydroxide, you'll need to remember to break it down into ammonia and water. Okay. Another thing to note is that you should memorize ammonia, NH3. So this is kind of the complicated, like everything's written down set of rules for this. Mrs. Treese and I decided to break it down for you. So essentially what we do is we start with the molecular equation, make sure to balance it, make sure to list everything as its solubility. Second, we're going to write the complete ionic equation. So essentially what you do is you're going to go through and you're going to ionize, so break it apart into its ions if it is soluble. Otherwise, you leave it together. And then third, you're going to write your net ionic equation. So essentially, for your net ionic equations, you cross off anything that is a duplicate on both sides. So those would be your spectator ions, and rewrite that equation. So let's actually put this into practice. Now, this is actually going into a lot of depth in terms of what we're actually looking for a question that you could see on the AP exam. So here it says solutions of potassium sulfate and barium nitrate are combined. So the first thing that we're going to need to do when we're writing our net ionic equation is to write the balanced equation. So I was told I have potassium sulfate. So potassium is K. Sulfate is SO4. We got to cancel out our charges. So K2SO4. Potassium has a +1. Sulfate has a -2. Swap, drop, reduce. And we are told that that's a solution, right? So aqueous. Plus barium nitrate, so BaNO3, 2. It is also aqueous because they told us solutions. It is going to go to produce KNO3 plus BaSO4. All right, so that would be the equation. Now, here's the thing. We need to make sure that we go back in and balance it. So I have 2 potassiums on the left and only 1 on the right. So I'm going to put a 2 up here in the front, and that's going to make it where I have 2 potassiums on the left, 2 potassiums on the right. I've got 1 sulfate on the left, 1 sulfate on the right, 1 barium, 2 nitrate, 2 nitrate. It's completely balanced. Okay. So now what I need to do is, actually go back in. Sorry, I wrote this wrong thing up here. And check my solubility. Okay, so for my solubility, because they've already told us the reactants, right? For my products, when I'm looking at my solubility, I need to think about my solubility rules. So the first thing I should ask is this, KNO3, an acid or a base? No, it's not. It's not an acid. Doesn't start with hydrogen. It's not a base. Doesn't end with hydroxide. Okay? So it's not an acid or a base. Is it an ionic compound? Yes, it is. We got a metal. We've got a polyatomic ion. So we do know that we need to check our solubility rules for our soluble salts. So for that, first off, we ask, is there something from group 1 or ammonium? Yes, there is. We know that everything with group 1 or ammonium is soluble, so this would be aqueous. Okay? Next, so since I know that one, I can move on to my barium sulfate over here. So first off, is it an acid or a base? No. Is it an ionic compound? Yes, it is. Since it's ionic, we need to look at our soluble salts, so the solubility rules. So first off, is anything from group 1 or ammonium? No. Any nitrate, chlorate, perchlorate, or acetate there? No. Any chloride, bromide, or iodide? No. Any sulfates? Yes. Sulfates are soluble unless they're paired up with silver, lead, mercury 1, calcium, strontium, or barium. It is paired up with barium, which means it is insoluble. So we would put that is going to be S, a solid. Okay, so now we've got our complete balanced equation, that complete balanced reaction. So let's actually move on to our next step. So the next step is to write the complete ionic equation. So the complete ionic equation, what I'm going to do is I'm going to actually go in and separate each of these ions out if it was aqueous. So here I've got 2 potassium, and it is the ion, right? I'm separating into its ions. So potassium has a positive charge, plus 1 sulfate ion, sulfate's a -2, plus barium, we know it's aqueous, so plus 2, and 2 nitrates, they've got a -1. And one thing we should be going back in and doing is putting what state of matter this is in. So this is aqueous, so we're just putting AQ there. It's just dissolved in water. We're going to keep on going. So go to the other side of the equation. I have 2 potassium plus 2 nitrate. Both of these are aqueous. Now, my barium sulfate here, we know is a solid, which means it was not aqueous, so it did not separate into ions. So this is going to stay as it was. All right. So now I've got my complete ionic equation. Next, I need to do my net ionics. Now, for my net ionics, I need to find my spectator ions and get rid of them. Okay, so I personally like to look at my complete ionic and cross off the things that are duplicates on both sides. So looking at this, I've got 2 potassium on the left. I've got 2 potassium on the right. So I'm going to go ahead and cross those off. Those are spectator ions, so they are not participating in this reaction. I've got sulfate on the left, but it did change, so it did something. Barium's on the left here, but it changed again, so something happened. Nitrate's on the left and nitrate's on the right, so it is also a spectator ion. So now I've crossed off everything that's a duplicate on either side of the equation. So then I need to go back in and rewrite the equation with just my participants. Okay, so here I've got SO4 with the -2 charge, which was aqueous, plus Ba plus 2, which was aqueous, and that produced BaSO4, which is a solid. Okay, so that would be my net ionic equation. Now let's list our spectator ions. So our spectator ions were the potassium ions and the nitrate ions. Okay. The very last thing to do here is what we call a beaker representation. So essentially what this is doing is it's listing out each of our ions that we have. So for my beaker that had K2SO4, I had 2 potassium ions and 1 sulfate ion. Okay? For my beaker that had barium nitrate, I had 1 barium ion and 2 nitrate ions. Okay? And then when we produce that, we did produce a precipitate, which was a solid. So I'm actually going to draw that down here on the bottom. So this is actually going to be BaSO4 floating down here, or sitting down there at the bottom. And then my ions are still, the spectator ions, they're still going to be floating around in the solution above. So I've got 2 potassium ions that did not participate, they're spectating, and 2 nitrate ions. And so in terms of my, sorry, it was freaking out. In terms of my beaker representations here, I'm showing those ions and I'm showing where they would go and how many of each thing I would have. Okay, so here would be our final representation of that reaction. Okay, so now what I want y'all to do is I actually want y'all to pause your video and attempt this next problem. Okay, so pause your video, attempt this next problem, and then we will go over it together. All right, so let's take a look at this net ionic equation. So first off, I needed to write my balanced equation. So it says, will a precipitate form if solutions of barium acetate and lithium phosphate are combined? So first off, I need to write my balanced equation. So I found that I had 3BaC2H3O2, 2, which was aqueous. They told us that we had solutions of it, plus 2Li3PO4, which was aqueous, and that produced barium phosphate, Ba3PO4, 2, which is a solid because it is not a soluble salt. And then I had 6LiC2H3O2, which was aqueous. Then I took that and I wrote my complete ionic equation. So for my complete ionic equation, the first off is to look at this barium acetate. So I did know it was aqueous, so I separated into my barium and my acetate ions. I had 3 bariums and 6 acetates. So I found 6 because it was the 3 times the 2 over there. Okay. Get rid of that. Then I moved on. I had 6 lithium ions. So now I'm on my lithium phosphate here. So I had 6 lithium ions and 2 phosphate ions. Keep moving on. My barium phosphate did not dissolve. It was not soluble, and so it stayed as a solid. Plus, my lithium acetate was soluble, so I separated it into its ions over here. Now, one thing I did forget to do right here is to put that charge. That is important. You will not get complete credit. You will not get credit if you do not have that charge there. So make sure you put that in there. Now, I would then go in and cross off my spectator ions. So I'm crossing off my acetate and lithium because they are on both sides as ions. And then I go in and I rewrite my equation. So my net ionic equation was 3 barium ions plus 2 phosphate ions produced a barium phosphate, which is Ba3PO4, 2. Okay? And then for that, my spectator ions would be acetate and the lithium ion. Okay? All right, then I did my beaker representation. So my beaker representation, if we go back up, I started with barium acetate, right? So I had 3 barium ions and 6 acetate ions. So my beaker representation should indicate that. So coming down here, I have 1, 2, 3 bariums and 1, 2, 3, 4, 5, 6 acetates. So this would be the correct representation for that. Sliding on over. I had my lithium phosphate. For that, I had 6 lithiums and 2 phosphate. So I count up my lithiums. 1, 2, 3, 4, 5, 6. And then I had 2 phosphate. There are 2 right there. And so that would be the correct beaker for the lithium phosphate. Lastly, I come over here. Now I know that my solid, that insoluble solid, that precipitate, was the barium phosphate. So I put that down here at the bottom. And then I had 6 ions of lithium and 6 acetate ions as well. So then I count them all up and I have 6 of each. So then that would be the correct beaker representation for this. And so that is what we are seeing right here as the overall thing. Okay, So now y'all have done that. So I want y'all to do one more. So we're going to slide on down here. We've got sulfuric acid. So I want you to pause your video, solve this next one, do the net ionics. I got rid of the beaker representation for this one just to speed it up a little bit for you. All right, so pause your video. All right, so let's take a look at this. So it says sulfuric acid neutralizes a solution of potassium hydroxide. Now, for this, we do need to recognize that I've got sulfuric acid and potassium hydroxide. Sulfuric acid is soluble because it is a strong acid. Potassium hydroxide is soluble because it is a strong base, so we know both of those would be aqueous. Now, it did tell you that it was a solution of potassium hydroxide, so you could have immediately used that as an indicator of this being a solution. Now, it did not say that about the sulfuric acid, and so you do need to follow your solubility rules if they do not clarify it as being a solution. Okay, so here I've got my balanced equation. So I have sulfuric acid, which was H2SO4. It is a strong acid, so no clo-clo-brickle. That would be the SO in that. And so it is a strong acid, so it's aqueous. Then I've got my potassium hydroxide. It would also be aqueous. And it's going to produce potassium sulfate, K2SO4, which, thinking about my solubility rules, it has something from group 1, so it is also soluble. And then I'm also producing water. So is water soluble in water? Well, no, water does not dissolve in water. So it would just be a liquid version of the water. Okay? Now, being a liquid, it kind of falls in that same category of it is not an ion. This is a molecular compound here, and so it will not be separated into its ions. Okay? So I do have my H2SO4. I separated it into 2 hydrogen ions and 1 sulfate ion. Then I did the same thing with my KOH. I had 2 potassium ions, 2 hydroxide ions. That produced 2 potassium ions, 1 sulfate ion, and we were left with that 2H2O. Went back in, I canceled out all my spectator ions, and I found my final formula, my net ionic equation, to be 2 hydrogen ions plus 2 hydroxide ions is going to produce 2 water. Okay, and then my spectator ions were SO4 and K+. Okay, all right, so that would be our net ionics there. So next I want y'all to actually come down, and this is one more net ionics, but it's got a little bit different take on it. So I want y'all to solve this net ionics first, and then we're going to answer the question here in B. So I want y'all to go ahead and do your best on this. Solve part A. You know how to do that. That's just net ionics. Then move on to part B. You're going to have to think a little bit about what your answer would actually be, and then try to answer that question. And then we'll go over it. All right, so pause your video, answer the A and B, and then we'll go over it. All right, so let's take a look at this net ionic equation here. So first off, I did take my NaCO3, my sodium carbonate, plus my calcium nitrate, and I did find out that those were both aqueous. Why? Because they told me they were solutions, and they produce sodium nitrate and calcium carbonate. Sodium nitrate is soluble because it has something from group 1, and it also has a nitrate. And then I have my calcium carbonate, which was insoluble because it does not follow any of my rules for solubility. Moving down to the next one, I go through my complete ionic reaction. So I've got my 2 sodiums there, my carbonate, the 1 calcium, the 2 nitrate ions. Then we come over to the other side, 2 sodium ions, 2 nitrate ions, and then we have our calcium carbonate here. So we went back in, crossed off our spectators, and we should have ended up with with carbonate here with the -2 charge, plus calcium with this +2 charge, and that produced the CaCO3. So that would be the net ionic equation. Now the second question says the diagram below is incomplete. Draw in the species needed to accurately represent the major ionic species remaining in the solution after the reaction has completed. Okay, so you're like, well, how would I know? Well, let's look and see what we've got in this. So I've got 2 sodiums and 4 nitrates there, right? Okay, so 2 sodiums and 4 nitrates. Well, let's look back up here to this information they told us. So they say a student is given 50 milliliters of a solution of sodium carbonate of unknown concentration. To determine the concentration of the solution, the student mixes the solution with excess 1 molar calcium nitrate, this causing a precipitate to form. The balanced equation is shown below. Okay, so we already did the balanced equation. We've already solved for all that. Now, I will say here is a big word that they told us in relation to this. Okay, excess. Now, excess means what? Excess means that we do not run out of this. So we're going to have extra than what we would actually need for this reaction to occur, to use up all of the sodium carbonate. Okay, so if I've got my 2 sodium ions, okay, well, if you look back up here, we started with 2 sodium ions, right? Okay, I've also got 4 nitrates. Well, in this reaction, how many nitrates did we use, quote unquote? Well, we used 2, right? So that again reinforces that I had excess of that substance, that calcium nitrate, and so I'm going to have excess of that nitrate, okay? Then I come down here and I've got my solid calcium carbonate. Well, okay, so thinking about that, so far, what I've got in my beaker, I've got sodium ions, I've got nitrate ions, I've also got my calcium carbonate. So the only ions that are missing right now are calcium ions and my carbonate ion. But looking at this, I know that I've already got these, so I can cross these off. So it's one of these 2 over here. So which one am I going to add? Well, I started with my sodium carbonate, right? And they told me that they gave me 50 milliliters of that. They also told me that I had excess of calcium nitrate. So what that tells me is that I would have used up all of my carbonate. Why? Because my carbonate, that sodium carbonate, was not in excess. There was a set amount of it. The calcium nitrate we did have excess of. So what that tells me is that the carbonate cannot be an ion in there. So then I must have some calcium ions floating around inside of there. Okay. Now I would only put 1 because CaNO3, 2. How many extra nitrates did I have? I had 2 extra nitrates. Then I had my calcium there as well. Okay. So that would be what you need to do when you're thinking about it. Essentially, we were going to have to add either calcium ions or carbonate ions because we already had the others. But the calcium nitrate was going to be in excess. So that means your calcium ions are going to be in excess. So they should be represented in your particular diagram. Okay. Now, here's something to note. In any kind of particular representation, be sure to watch out for your limiting reactants, because your limiting reactants are going to be the ones that are completely consumed. There may be some left at the end if one of the reactants was in excess. So that's what we saw here, where we had to add that extra calcium because there was some excess calcium that was involved. Okay. All right. Moving on. So this one says the diagram below represents hydrogen gas and nitrogen gas in a closed container. Draw a diagram which represents the result if the reaction shown below were to proceed as far as possible. So essentially, we're trying to consume as much as we could. So this is what we started with our reactants as. We started with 3 nitrogen and 3 hydrogens. Okay, so we started with an equal amount of those. Now, looking at my formula, I know that if I'm making some ammonia, NH3, then I'm going to have 3 hydrogens, 1, 2, 3, and a nitrogen. Okay? 1, 2, 3, and a nitrogen. So now I've got that. But let's go back and let's check what our reactants were. So on the reactant side, I've got 1, 2, 3, 4, 5, 6 hydrogens. On the right side, I have 1, 2, 3, 4, 5, 6 hydrogens. So my hydrogens are good. On the left side, I have 1, 2, 3, 4, 5, 6 nitrogen. On the right side, I have 1, 2. Okay, well, that's not right? Remember, we have to make sure that both sides have equal amounts. So what we know is that we must have some excess of that nitrogen, which means we need to represent those in our particulate diagrams. So then that should be what our products should look like. Okay? All right, very last one. This one is a little bit tricky. What I want y'all to do is go ahead and give it your best shot. So pause your video, work through this, and then we will talk about it. All right? All right, so looking at this, this should have been what you got for your particulate diagram. So we should have ended up with 4 acetates and 3 sodium ions. And then we should also have 1 lead ion, 1 chlorine ion, and then our lead chloride at the bottom there. So how did I get to that point? Well, first off, let's remember that we do need to know what's going to be aqueous and what's not going to be aqueous, because essentially your spectator ions are going to stay towards the top of the beaker. They're going to stay in that solution. So I do know that my both of my reactants were going to be soluble, right? They told me that. So we could come back up here and put aqueous by both of those. My lead chloride, remember, if we follow our solubility rules, all chlorides, bromides, and iodides are soluble unless they're paired up with silver lead or mercury 1. So this was paired up with that, so that would be my precipitate. And then lastly, I would look at my sodium acetate here. Sodium is in group 1, so it is going to be aqueous. All right, so now I've got this. So I know my sodium and my acetate were going to be spectator ions. So all of those sodium and acetate ions needed to be represented in the ion form. I had 1, 2, 3, 4 acetates there. So then I come back over here, try another color for you. 1, 2, 3, 4 acetates there. I have 1, 2, 3 sodiums. So 1, 2, 3. Come back over here and check. 1, 2, 3. There's no others. And then you're like, okay, well, how did I end up with that lead and that chlorine that's floating around in there? Okay, so let's think about this. So I started with 1 lead and 2 acetate in my original formula, right? But when I look down here, I've got 2 lead and 4 acetate. So what that tells me is I have double the amount. So kind of like I'm saying I have 2 of those in this beaker on the left. Then the beaker in the middle, I've got sodium chloride. Well, looking at this, I've got 3 sodiums and 3 chlorines. Well, essentially, that's 1.5 times that 2, right? So I started with that 2 right here. I had 1 additional sodium chloride. So really, that's going to end up being a limiting reactant for us, right? So I did represent that right here. So what I know is that my sodium ions were spectator ions. So I'm going to need all 3 of those to be put in there. The chlorine ions were used to create that lead chloride, right? But lead chloride is PbCl2. I only started with 1, 2, 3 chlorine, right? So when I made that PbCl2, I could only make 1 of those. And since I could only make 1, the extra needed to be in the beaker. And so that's what I see right here. Okay, then I come back over here and check my lead. I had 2 of them. I used 1 of them because I only made 1 of that lead chloride. And so I was left with 1 additional lead. So I would put that lead as an ion in my final beaker. Okay, all right. So hopefully that helps. That is it for our lesson on net ionic equations. As always, let us know if y'all have any questions. Please don't hesitate to reach out. But otherwise, that is it. Y'all have a great rest of the day. Bye, y'all.